Before we leave behind the washer method, we want to do one more problem that kind of kicks it up a notch in terms of difficulty. So we want to find the volume of a solid generated by revolving the region bounded by the graphs xy equals 5. Okay, so xy equals 5 is this curve right here. It's solved implicitly as opposed to explicitly. So xy equals 5, y equals 2, y equals 5, and x equals 5, about the line x equals 6. So you'll notice I've got my axis of rotation kind of marked right here. That axis of rotation is what we're rotating around. But we're bounded by a bunch of different lines. So let's look at those. So we're bounded by y equals 2, which is right here. Y equals 2. Y equals 5, which is right here. And then x equals 5. So this is 4 and this is 6. So x equals 5 is right here. I love it when algebra comes in handy. Y equals a constant or horizontal numbers, x equal constant vertical, or vertical lines, horizontal lines and vertical lines. All right, so the region that's bounded by that curve and those lines is right here. Now, which way do I go with my rectangle? It's not really a choice. We're going to do this with the washer method. Therefore, our rectangle must be perpendicular to our axis of rotation. So this is kicking it up a level because we're going to do a vertical axis of rotation, and it's not even the y-axis. It's the line x equals 5. So we're going to go this way with it. So perpendicular to the axis of rotation. You can see, obviously, that the thickness is dy. No problem there. Washer method, well, actually, these methods in general are very obvious. Once you have your axis of rotation, if you choose to do the washer method or disk method, your rectangle must be perpendicular to that axis of rotation, which means ultimately you know that you'll be integrating with respect to y. It has to be. All right, if we're integrating with respect to y, that also tells us what our boundaries are, because we're going to go from this y value, that's our c, to this y value, which is our d. C and d being the pieces of the volume integral when we're rotating this around a vertical line of our axis of rotation, sorry. Now, the hard part, and it is quite tricky. We need to be able to find the radiuses. So let me kind of put in over here, actually let me give myself some space here, but I know that the volume is going to be pi integral c to d, and then it's going to be r of y squared minus little r of y squared. And I know it's dy. That's set in stone once I know it's the washer method and I know that I'm doing a vertical axis of rotation. Now, the hard part is going to be figuring out how to do this. I need to be able to find these radiuses, or radii. Okay, so let's think here. The entire distance from the y-axis out to the axis of rotation is 6, right? Now, the little radius is inside, and then there's the big radius. The little radius is actually really easy to figure because this is a set width. It's never changing. So the little radius is no problem. R of y is 1. Period, the end, no question about it, right? It has to be 1 because this is never changing. That's not a curve, it's a vertical line. So it's literally like a stack of DVDs where that inner hole is always the same. But I guess it's more like a chord apple because the outer part is not what's the same. This part is changing, so it's not going to be a set, and we need to figure out what that is. So if I say from here, that value to back to the axis of rotation, that's r of y, and I need to figure out a formula for it. All right, now the thing is that when we do functions in y or functions in x, they're always based from the axis. So the axis is over here, the y-axis. And so that distance from that axis out to that curve right here, that distance right there, if I'm going to solve this for x is, oops, sorry, you can't see that. X is 5 over y. That's a function in y. I'm just going to call it f of y right there. It's not r of y. It's not the radius. It's this piece. So this is f of y. It's 5 over y. Now, why did I say 5 over y? Why didn't I solve it for the other one? Well, because I know I want these functions to be functions in y. I know that I'm integrating with respect to y. So there's no point in solving it for y equals 5 over x. It's true, but I don't need it. What I need is 5 over y. I need this to be a function in y. But that all functions are based back to the x-axis or the y-axis. In this case, since it's a function of y, it's going back to the y-axis. So if you think this little piece right here is 5 over y, right? That's f of y. So r of y, this radius, would be 6. Take away this little pink part, right? This whole distance here is 6. From the y-axis all the way out to the axis of rotation is 6. And then this little part right here is 5 over y. So if I take 6 and I take away 5 over y, I'll have the r of y left over, like that, right? And then this little r of y is easy. R of y is 1. And this one right here is what I was just saying. It's 6, take away 5 over y. Let's just let that sink in just a little bit. Okay, one more time. The distance from the y-axis out to the axis of rotation is 6. So that's 6. Take away this bit over here. So I want to take away this little part over here. That's taking away 5 over y. So 6, take away 5 over y will get me this distance right here. And then 6 minus 5 over y, take away the 1, will get me what I'm looking for. So the volume will be equal to pi. The c value we said was 2. That's c right there. C is 2. D is 5. Those were actually given in the problem. And the hardest part by far is finding that capital R of y. So it is 6 minus 5 over y. Minus, and then the little inner one was 1. So that's pretty easy. So we make up for the really hard capital R of y by a really easy little r of y. All right, now what is that? This is pi integral from 2 to 5. Actually, I'm going to leave those as pink numbers, sorry. So this is 2 and this is 5. When you FOIL this, it's 6 minus 5 over y times 6 minus 5 over y, which is 6 times 6, which is 36, minus 5 times 6 is 30, and there's 2 of them, so 60 over y plus 25 over y squared, minus 1, right? I can do that. 1 squared is 1. Even I can handle that. Right? Again, to do this, I'm just FOILing, right? Just distributing out, right? 6 times 6 is 36, 5 times 5 is 25, the y's get squared, etc. All right, so this is the integral from 2 to 5 of 35, take away 60 y to the negative 1 plus 25 y to the negative 2. Right? Okay, so doing some work here. That's pi times 35y minus 60 natural log of the absolute value of y plus 25, oh, minus 25 because it'll be minus 25 y to the negative 1 because we add 1 to the power, then multiply by the reciprocal of that power, which will turn the plus into a minus. And we're going to take that from 2 to 5. All right, so I would make Desmos do this. Yes, this is not worth our time to be mucking around with this. It just isn't. So we will make Desmos do it. Let's see how we can make this happen. Oh, and there's the picture in case you're interested. All right, let's see what I showed in here. Meh, that's not enough work. All right, so if I say, let me just name these functions. So I'm going to say h of y is equal to 35y, I'm just using that integrand, 35y minus 60 natural log of the absolute value of y. The absolute value actually won't matter to us because -1, or excuse me, +2 and +5 are both positive, so it doesn't really make any difference. So if we want, we could say just y in this particular instance. Okay. And I don't really want to graph it, I just want to look at it. So then h of 5 is that value. H of 2 is that value. Oh, and I got to multiply the whole thing by pi. I forgot about that. There we go. So I can find each of these values and then just subtract them. So 230.69, oh, why don't I just do it this way? H of 5 minus h of 2. And I'll tell you whether or not my integration is correct because it should match the integral that I found above. And it does. It's 180.712. Hooray! So we will just do that with Desmos. We're not going to be able, we wouldn't be able to find an exact answer. I mean, we could, but it's not worth our time. So we will just say it's 180 point, oops, I got weird, 180.712 meters cubed. And we'll just say what we used to find that.